perhaps we could start the meeting just by asking you to give us a brief introduction on yourself and your work on drones, your interest in drone technology.
Okay. Yeah, sure. Thanks again for the invitation, Jim. So I'm Henrik Hesse from the University of Glasgow, based in Singapore, and I'm leading the aero robotics lab over here. So I'm working a lot with drones, with UAVs, and the idea is I'm working a lot with industry partners to see how we can use drones and UAVs as tools. So looking at industrial applications, and then in my role, basically looking at challenges, right, that we face using drones. So if we're looking at indoor applications where we can't use GPS, so I'm developing ways for GPS denied navigation. We're also adding intelligence to drones, so anything that we need to do to detect obstacles, or allow drones to actually do inspection tasks using computer vision and all this. So I'm looking into this. And the final part is to design more efficient platforms. So this is looking into design methodologies and anything that we can do, looking at aerodynamics, the structure design, and so on, to basically develop more efficient platforms. And this can be heavy lifting drones, or air taxis, or small industrial applications.
Yeah. Okay. Fine. And I'll introduce myself, Henrik. My name is Jim Casey. I work for the Malin Group in Glasgow, and I'm in charge of a small Skunk Works team. And our interest in drone technology at the moment is to look at the art of the possible for heavy lift drones. And by heavy lift, we're looking at payloads in the range of 1 to 25 metric tons. And that's one of the reasons through your published papers that we made contact with you. So perhaps we could just continue our discussion around drone technology. Would it be possible just to take your view on the current status of drones and the individual key components such as battery technology, aerodynamics, motors and propellers? Because my understanding is that commercial drones, as opposed to military drones, probably have payloads in the low numbers of kilograms, and the occasional drone publication indicates that some are being developed with payload capabilities in the low hundreds of kilograms, but would be very interested in your view on that.
Okay, yeah, that's a good point. So let me just refer back to the paper that you mentioned on design methodology for heavy lifting drones. I think that one is nowhere close to the numbers that you mentioned. So we only looked at a few kilograms, but this already moves into what we consider heavy lifting market, because it's more than the hobby market that we have, right? If you have a hobby drone, the payload is typically just the weight of a gimbaled camera system.
Yes.
So as we're looking into more industrial applications, this is where where originally a few years back we actually considered this heavy lifting drones. And when we wrote this paper, when we started this work, we saw that there's actually a lack of design methodologies. So of course we all know the drone companies. We have famous one, DJI or Parrot, and then they have developed drones, and I'm sure they have a design team, or they had 5-10 years ago they had a design team in-house, but there was no standard methodology like we have for aircraft, like conventional aircraft design. So this is what you mentioned, right? So design methodology would need to include the propulsion system, the energy storage systems, the wing design or the aerodynamic design, and in the end the structure design. So all these things come together when we design a conventional aircraft, and this is what we thought was missing for multi-rotor drones, and that's why we started looking into this direction.
Yeah.
So I think what you mentioned is, what are the key technologies, right, that we need to explore? I think the obvious one is a lot of the multi-rotor platforms are electric, right, electric propulsion systems, and the limitation there is the energy density of batteries that we have. I'm by no means an expert in that area, but that's probably, I mean, that's something that, you know, we already talked about is critical. If
Yes,
we
very
want
much
to,
so.
you know, be able to actually develop platforms that can carry, you know, heavy weights or actually fly for a long time, operate for a long time.
Yeah.
But the other things that I'm interested more would be, of course, the aerodynamic design, the structures, and how everything comes together when we talk about the propulsion system. So specifically, if we have multi-rotor drones, right? So we don't have any aerodynamic surfaces as yet, right? So we're just talking about pure vertical takeoff and landing VTOL platforms without wings. We basically see we have the propulsion system, and we need to have a very light structure, right?
Yes.
To basically house the propulsion system and any payload and the avionics system and so on that we want to operate. So there we see that actually the platforms that are being developed look at, you know, the latest technology that we have, and since all these platforms are unmanned, or most of them, right, we can actually use really nice novel materials, which would be, you know, much lighter and stiffer compared to what we typically see in, you know, conventional aircraft applications.
Yes.
Right, so talking about carbon fiber composites and these sort of things, of course, that found their way already into conventional aircraft, but I think actually it's a really good playground to use them for, you know, heavy lifting drones.
Yes. Yeah.
Right, the lighter the structure, the more payload you can carry, of course, and the longer you can fly. But there comes the difficulty is to simulate, right, all these, the structure, for example, and then later on talking about the aerodynamics and propulsion as well. So how do we design such a structure without much experience, without a methodology, and with simulation capabilities that take a long time?
Yes.
Letting Fergus back in again.
Yeah.
Okay, so
Yeah.
these are the challenges when we're talking about the design, right? It's basically we need to have a simulation tool for the design methodologies that can simulate the structure, which is made of,
Yeah.
you know, complicated materials such as carbon fiber composites, and at the same time we're looking at very complex flow phenomena, right? So we have the propulsion system, which tends to interact with the structure. So
Yeah.
something that I'm interested in is, of course, to look into the fluid structure interaction for such platforms. We can simulate this. We can get pretty good numbers just in simulation, but it takes days to solve that.
Okay.
So if we want to use those results to design, you know, new platforms, that's not feasible. So
Okay.
I think in short, what it means is we need to build the experience in designing these platforms with simulation and experiments, draw conclusions, you know, use model reduction techniques, probably even machine learning or whatever, goes into, you know, developing new design methodologies such that we have efficient tools for, you know, specifically for design of multi-rotor vehicles.
Yeah. Yeah. Okay. With the existing technologies and the current market incumbents, do you feel that there is one area, be it structure, be it energy density of the fuel source, be it the efficiency of motors or the design of the multi-blade propellers? Do you feel that there is one area which is more advanced than others? And the other obvious question is there any of those areas that based on your review of the marketplace and understanding, that is lagging behind the others?
Okay, good question. I mean, okay, from the different areas. So what I think is we talked about the structure, right? So I think looking into again, I'm not an expert in carbon fiber composite materials, but I do see that, you know, looking at design of very light structures that can carry, you know, lots of loads, that this is an area that has been sort of explored already. And you see the platforms that are being developed, you know, they actually are very light and stiff. So I think that's an area which is promising. The other one is the propulsion system. So it's interesting to see that, you know, historically we've come from, if we talk about the 1940s or something, from multi-rotor designs, which then were not continued anymore. We, of course, no helicopters, so we have one main rotor and a tail rotor, which has been basically the state of the art, up to recently, to have heavy lift platforms. And now suddenly we see this, a trend towards multi-rotor vehicles. And I think that's actually a really interesting area where we need to understand more. So, what is the efficiency of these platforms? I mean, there are advantages of having a distributed propulsion system. So this is what we're currently seeing. For example, if we talk about air taxis, and I'm sure this technology will move over into heavy lifting drones as well for carrying goods. Right, so we have this trend of the distributed propulsion system, and the advantages are there, I guess, in terms of safety, in terms of availability, what's currently available in the market for electric propulsion, and so on. But there remains the question mark on what's the aerodynamic efficiency of these distributed propulsion systems over just having a large, very efficient rotor like we see in helicopter platforms.
Yes, okay, yeah, and my limited understanding of the aerodynamics is that the contra-rotating systems provide the torque reaction and remove the need for what would be the traditional tail rotor in a helicopter. But my own feeling, I guess, is if we look at potential air taxis where we have a human cargo and thus the safety factor is paramount, then I guess the redundancy factor in terms of failure modes becomes very, very critical. But at the moment, we have helicopter systems which are accepted with very limited redundancy. What a single main rotor requires only one failure or a failure of the tail rotor for a catastrophic event to occur. And do you think that that acceptability will transfer across to things like air taxis?
Yes, I think that's one of the advantages of having multi-rotors, right? And we have so many examples for air taxi designs that are currently looking at a multi-rotor system. I think one of the reasons is this redundancy, right? I've seen lots of our drones that we've developed, multi-rotor drones, crashing, and most of them, well, there's some bad crashes, but most of them actually crash nicely in a way because of that redundancy. So you can have a coaxial system where, as you said, right, the torques balance each other out. So if one coaxial rotor fails, the platform can still land safely with the remaining rotors intact. So all these things, I guess, make it more attractive to have a distributed system. But as you said, I mean, actually, we have helicopter platforms. They're certified, right, to be safe. There's a certain level of redundancy there as well, and capabilities to land even, if the main rotor fails, if the propulsion fails. So we have this in place, but to summarize, I do think that an advantage of having multi-rotor platforms is that safety aspect.
Okay, and I guess that there is also the question of maneuverability in multi-rotor platforms, where you still retain a significant degree of maneuverability rather than just the ability to control the descent.
Yes, yes. I mean, that's it's much easier to fly a multi-rotor than a helicopter. And I'm thinking with all the flight control design that we're doing to basically just have hobby drones that any amateur can fly to professional applications. If this translates to air taxis, then again it makes for a much safer platform. And I think the other aspect is if you have smaller rotors, it's less scary, right? If you're operating, or if you're a human operator next to these platforms.
Yes.
So we're looking at, if you're thinking of carrying goods from shore to a vessel, close to shore or something, right? A ship, and you have these drones landing close to human operators, and everything is, you know, unmanned, fully autonomous. Personally, I would feel probably safer next to smaller rotors compared to a large helicopter platform.
Yes.
And it's easier as well to shield the rotors, so using propeller guards or you know, ducts. So if you have a smaller diameter, it's still feasible to actually put a propeller guard around you know, the rotors, as opposed to a helicopter, right? You can't have a large
Of
guard
course.
around a
Yeah.
helicopter. So all
Of
these are
course.
things that are currently, I guess, more attractive. And that's the reason why multi-rotor platforms are explored, right, for air taxi platforms.
Okay. In our previous discussions, yeah, you made a very valid point about the difficulty associated with a change in the load or the position of the load within the drone cargo compartment.
Yep.
For heavy lift items, that's potentially less of an issue, but for personnel transportation, then if you have more than one person, then it becomes a fairly significant issue. Do you have a feel for the impact on the efficiency and the load carrying capability of a multi-rotor drone if it always has to cope with the worst potential load distribution? Does it become 50% less efficient? Does it have to have a 150% additional capability that may or may not be utilized for a small or large part of its operating cycle?
Yeah, that's a very good point. I should have those numbers. I think if I were to design a platform and sell it, I should definitely have those numbers ready. Yeah, just to summarize, so we did look into this. So when we're designing a multi-rotor vehicle, right, we're looking at the weight distribution. If we have a quadcopter, we want the center of gravity, so all the loads to be centered, such that the four rotors basically do all the same work. That's the easiest configuration we can have. So the things that we talked about last time. Now, what happens if a passenger gets off and the, you know, the weight shifts slightly, let's say forward, the center of gravity shifts forward because of this. Or actually, let's say we have a passenger coming on. That's a better one. So the center of gravity shifts forward. That means the craft is nose heavy, and the front rotors have to work harder. And then it's a question to what's the design envelope for these motors or these rotors? So if we design them to be the most efficient, right, the operating point to be most efficient at say 50%, right, and then we have this nose heavy configuration that suddenly the front rotors have to work harder and they operate at 65%. That may not be the most efficient operating point anymore. So I can't give you the numbers to prepare this. But I think it comes down to how you want to design your vehicle and what are your operating points. So we saw this, you know, if you have these shifting payloads, it's a disadvantage. So for sure, your drone may not operate anymore at the most efficient point. And that's why we looked into having a morphing platform such that you can adjust the drone platform itself so that, you know, instead of moving the payload around inside the drone, you actually adjust the vehicle itself such that it's self-balancing. And I have to give credit to the company I was working with. So this is the work that we did together with Nimbus UAV in Singapore here, and they actually have patented this technology. So last time we talked, this was for a delivery drone. I think, as you mentioned, right, this is very relevant for passenger drones, right? If you have you know, passengers coming on and off, yeah, or if you're just delivering goods.
Yeah. Okay. And in terms of a heavy lift drone or a variable capacity lift drone, do you think it's feasible not only to change the geometric configuration of the drone, but perhaps to add additional lift capability by adding an additional arm with an additional rotor set or two arms to counterbalance?
Yes, I mean that's a really good idea, right? I think it comes down to the weight that you're adding,
Yeah,
and then this goes back to the design methodology that I talked about earlier. So it's always a compromise, right? Basically, if we see that, let's say if the platform, the drone is off balance, and the original motors are operating at not the optimal operating point anymore. So what is this drop in efficiency? And then would this justify the additional weight of the rotor? And actually, with the work that we're doing on the design methodology, you can actually just do these, trends, and you can see, okay, what is the, the shift in the center of gravity that causes this off balance, and then where is it more useful to have additional rotors
yeah,
with the weight, or where is it more useful to have a morphing platform, which of course adds weight as well,
yeah,
and so on. So yeah, I think because it always depends on your design requirements, right? It depends on how much weight you want to deliver. Um, what's the flight time of the drone, and all
yeah,
these things come together. So that's why it's useful to have such a tool.
yeah.
Or
Okay.
it's essential.
In terms of the balancing between lift capability and range,
Yeah.
has your work developed any feel or any guidance on is there a sweet spot where you have the maximum lift capability for a given range? Can you tell us anything about that?
I mean, so the what we're seeing, right, is if we have a multi-rotor configuration, just a quadcopter drone, the ones that we can buy now off the market for hobby applications or industrial applications, their flight time is typically around 20 minutes, 40 minutes, and they're pushing it to about maximum 1 hour. If we're looking at pure electric propulsion, so not looking
Yes.
at any hybrid or fuel or anything. So I'd say the limit would be 1 hour probably, right? So not many platforms have achieved that target, and it's always a trade-off, right, between the endurance you want and the payload you're carrying. But let's say 1 hour would be the target. Um, if you want to, if you have applications where you want to fly longer, if that's what you want to do, or cover larger distances, that's then where you would have to look into additional. Well, it's not a technology; it's just adding a wing to it. It's something that we know from the history of flight for hundreds of years, 100 years.
Yeah.
You have a wing, right, which is a much more effective, efficient way to carry your vehicle than brute force propulsion system. So,
Yes.
right, if we're looking at a wing, I think we talked about this last time. Is if you're generating lift through aerodynamics with the wing, and you're looking at the aerodynamic performance, we typically see numbers like a wing generates 10 times as much lift as drag, right?
Okay.
So
Yeah. Yeah.
basically, if you want to fly, longer distances, what you have to do is you just have to produce thrust from your propulsion system to overcome your drag.
Yes.
So if you're looking at the weight of your system, basically what it means is your lift from the wings balances the weight. So the drag is only about 1/10 of it, or depending on the
Yeah.
aerodynamic efficiency of your design. Um, so the drag is 1/10, which means the thrust required is 1/10 of your 10% of your weight. Whereas if you're
Okay.
looking at a
Yes.
pure multi-rotor platform, um, the thrust required is 100% of your weight. That's
Yes.
just pure propulsion. Um, but your wing adds weight to your system. So again, it comes down to what is the design requirement. If you want to fly for half an hour, short range, it doesn't make sense to add a wing to your structure,
Yes.
because it's probably just adds weight, and you have to first carry this additional weight to your target altitude, um, and you would just burn you know more energy to achieve that.
Yes.
Okay, so this comes down again to the design methodology. So at some point, when you basically draw your curves, there will be a point where it's more feasible to have a fixed wing structure with a VTOL capability on top.
Okay, and some of the commercial delivery drones available at the moment, they use a vertical takeoff capability, but then they rotate the propulsion, the nacelle and the propeller effectively to generate forward motion over an aerodynamic surface.
Yes.
Is that feasible with a contra-rotating ducted rotor set, or does it require a single propeller?
Okay, good point. Have you seen any designs that uses a coaxial counter-rotating system
No,
that has a tilt rotor?
only a single propeller.
Yeah, only a single one, right?
Only a single propeller, yeah.
Okay. I mean, the question is, when you have a tilt rotor configuration, so when you're talking about the VTOL, the vertical takeoff and landing phase, you have all the rotors working, fighting hard to produce the thrust to take off.
Yeah.
If you're then tilting that rotor and you use it for the forward flight phase, you only need a minimum amount of thrust to overcome your drag. So that rotor would work at a very different operating point compared to the takeoff phase. Again, if that operating point is the most efficient for that forward flight phase or not, that's the question. But actually, it's a good point. I mean, you could have a design where you have a coaxial system, which it doesn't produce twice the amount of thrust compared to a single rotor, but about we see about 20 to 30% drop. So a coaxial system would produce about 1.8 times the thrust of a single rotor. You could tilt this one, and then the lower rotor in the coaxial system could actually stop, right? You could kind of fold the propellers back, and then just have the top rotor spinning to provide thrust in forward flight over. I think that would be really cool designs you could come up with.
Yes, yeah, I understand. I understand the concept. Yeah,
that's actually a good point, right? Because in forward flight, you only need about 10 or 15% of the thrust that you have compared to takeoff. So if you have a 4 coaxial rotors, 2 of them tilt forward, but actually then the bottom part kind of folds back.
Yeah,
you get your 20% already. Okay, yeah, that's a good idea.
Yeah, yes, it's an interesting concept.
That. Yes.
Yeah, it's a very interesting concept. Yeah, in terms of the motor technology itself, I am no leading expert in motor technology, but I'm assuming that the efficiency has a significant part to play in terms of duration, if not the lift capability associated with the rotor pack. Have any of your investigations come up with a motor technology that is preferable or more efficient than any other?
No, I'm completely lost. So the motor technology is something that for myself, I consider off the shelf. So we have capabilities to basically evaluate the efficiency of the motor. But I wouldn't look into motor designs or technologies. What we're seeing is that, again, with the multi-rotor, so the hobby market, right? We have small quadcopters. Of course, they've gone up in size, and with this, we see that we have a lot more suppliers that can actually provide very efficient motors.
Yeah,
and it's interesting to see, the motors that we're buying for our smaller industrial drone platforms. And then actually from the same supplier, we can see that they're providing motors for kind of air taxi platforms.
Okay,
like
so
a lot more powerful,
significantly more capable. Yes.
Yes.
Yeah. Okay. Okay. In terms of the energy sources, we've spoken mostly about batteries, and trying to combine those thoughts with the ability to combine vertical lift with forward flight over an aerodynamic surface. Do you think it would be possible to look at the hybrid battery technologies where we have some supercapacitors providing the boost for the vertical phase, and then the cruise phase, which is requiring 10% of the vertical lift power requirement, could be supplied by the more normal lightweight battery technologies?
Yeah, absolutely, yes. Again, I'm not an expert in battery technologies, but what I see is that we have two distinctly different operating points for the aircraft, for the design, right? And as you said, we have during the takeoff and landing phase, we require a lot of power, very quick discharge of whatever this energy supply is, right? Versus in the cruise condition where we have the extended operation, we require very little thrust, and we don't have much variation in that power requirement.
Yeah.
So I absolutely, yes, can imagine that if we have a hybrid supply for those two different phases, that it makes the most sense.
Yes. Okay.
Whatever this technology is, right? I mean, you could also say that we could have a fuel-powered takeoff phase versus just electric propulsion during the forward flight phase.
Of course. Yes. Yeah. Okay. You make a very interesting point there. In terms of the power requirements, do you have a view on the power required to take off versus the power required to control the descent? Obviously, gravity is working with you in the descent phase and against you in the takeoff phase. But do you have a feel for what those numbers might be as a percentage of each other?
Okay. Yeah, I mean, I'm not a drone pilot, or there are lots of other cool guys out there that fly drones and design platforms from the hobbyist part. But typically, what we say is that if we design a multi-rotor, is that we want to hover at 50% throttle to allow excess thrust for takeoff or maneuvering around. So this is the typical sort of benchmark. If we're looking at a more sluggish design, we can actually hover at 60%, 65% throttle. But if anything above this, so if we have a really heavy platform, and we are underpowered, we would not have excess thrust to actually take off.
Okay.
So that's the typical. Yeah, I'd say when we're flying, so you take off. We don't see much of a variation. So we have basically the excess thrust for takeoff, but it goes up to 60-70% of the thrust level, and then it would vary down when you're doing a descent. But because it's a controlled landing, the throttle levels for the descent are not much lower than your typical hovering levels. So you would go down to 40% or something.
Okay, that's interesting. Yeah.
Right. But it's a good point. Is I don't know what is the additional power for takeoff versus hovering or landing.
Okay. Yeah.
Those are actually interesting numbers to look at.
In some of the drone applications on the marketplace at the moment, the use of external mechanical energy input is used at typically a catapult system, which implies an aerodynamic surface in some way. Do you think there is any possibility of using mechanical assistance, stored energy assistance in the vertical takeoff mode? The obvious would be a coiled spring, which is then released and effectively fires the drone vertically upwards. But I'm sure there are many more sophisticated pneumatic and hydraulic systems we could apply there. But is that something that's been looked at?
I haven't looked at this myself, but actually it's a good point. I mean, it comes down to the design that you have. I would think, right, if you have a pretty compact, let's say, multi-rotor quadcopter design, where you don't have any lifting surface and these sort of things, from a structural point of view, it's feasible, right? Because it's a very dynamic maneuver.
Yes.
Where you're accelerating the vehicle at a high rate, so if you have any sort of slender structures like wings that are designed for nice aerodynamic forward flight, I don't think it's a good idea to catapult it up at very high velocities. But of course, I mean, this is something that we see, right? If you're looking at fixed wing designs, for agricultural drones, and there are commercial solutions out there that actually look at controlled catapult launch, which is possible for fixed wing as well. But anything more aggressive than this might probably produce loads on the wing structure, which then again you need to design those wings to withstand those dynamic maneuvers or launches, which again would add weight to the platform.
Of course, and yes, absolutely. I guess it comes down to the ability to control the rate of the vertical rate of acceleration, to match the structural capability of the vehicle. Yeah.
Yes.
Yeah. Well, one of the things we've been looking at for heavy lift drones is the ability to split the energy source, where the drone vehicle itself only has sufficient energy to fly in the unloaded condition, and the load or the load container actually contains the additional energy required to fly in the loaded condition, such that when the load or the load container is on the ground, the internal energy source can be recharged. And when the drone is on the ground, the drone energy source can be recharged. But when you fly the drone unloaded, it has sufficient energy to reach the load. And when you fly the drone loaded, the load itself contributes the additional energy required to reach the destination. I don't know if you've ever had any thoughts on that as an aspect.
It's a great idea, and I hope you have patented this already. I think it's amazing, right? To think that your payload comes with its own battery, basically, right?
Yes.
Which is amazing. Yeah. I think that makes total sense, right? Because for any payload that you want to carry, if it's a modular platform where you can have different payloads that you're carrying, you of course need more battery power if you have more payloads for the same endurance. So that's a really good idea.
I also think that for us, it potentially opens up the opportunity for different energy sources. Battery and interchangeable batteries are the obvious choice. And when we get to significant multiple ton payloads, then the battery technology starts, at the moment, it starts to resemble that used in the automotive industry. We're looking at those kinds of numbers, 1 and 2 ton payload numbers, and batteries that are capable of driving those for many hundreds of kilometers. But our thoughts are also looking at some, say, potential for the use of hydrogen as a fuel, and the ability to incorporate that into the payload in some way reduces the physical space requirement on the drone, because the unloaded drone condition would always be battery powered, but the loaded drone condition can use a fuel of much greater energy density.
So the payload would come with its own fuel cell in this case?
Potentially, yeah. We're very much just looking at what the art of the possible might be, and in some ways we have to think in a fairly unconstrained fashion. Otherwise, then we immediately become constrained by current technologies. But if we think a little bit more out of the box, then the opportunities for alternative fuels, and particularly those which are still seen as very green fuels, as hydrogen most certainly is, then they start to offer some additional opportunity for greater energy capacity, is possibly the best way to put it. Yeah.
I think that's a really interesting topic, because when we look at the design of multi-rotors in this case, or actually fixed wing aircraft as well, we always look at certain trends, right? I mean, right now, basically, if I look at the market, I can tell you that if I look at any drone, that typically can carry 1/3 of its total takeoff weight as a payload. The other third is typically the battery, and depending on the structure, the remaining 40% would be the, just the frame and the electronics and everything else itself, the propulsion system. So the empty weight of the drone. So actually, we see that the endurance and the payload is always a trade-off between the two of them, of course, right? So you can replace payload with additional battery to fly longer, or the other way around. If you want a very heavy lifting configuration, you could replace batteries with payload, but of course at the cost of not being able to fly as long endurance. So you say that your payload comes with a battery directly. That plays directly into that balance between payload and endurance.
Yes, and the option of having the battery or the hydrogen fuel cell or whatever energy source we choose, having that as part of the payload, then in a modular system you can in fact have payload containers which define both the payload and the endurance as a trade-off. So you can have a series of sub-modules where you have a larger energy source and a smaller payload, or vice versa.
That's an awesome idea. Yeah, and then you have the you solve the problem of the battery swapping as well. I mean, that's something that's currently done. Is you just have a box where the drone can land and where it's housed, protected from the weather, and then these boxes typically would include the charging or the battery swapping. And so on, right? So actually, with your payload base, you could do that as well.
Yes, we could. Yeah, we could. If we take a moment to look perhaps a little further down the road, the rate of development of drone technology, I would assume, has been fairly rapid in the more recent years. But do you have any thoughts about what the future might hold? People often talk about 1 year, 5 year, 10-year cycles, but if you look at potentially air taxis as possibly the first option of what we may address as a heavy lift concept, do you have a feel whether we're looking at 5 years, 10 years, 20 years before we get to the next phase?
Good. We should call Elon Musk and ask him what's the future he will have planned for us. No, but it's true actually, because I just realized that DJI drones and so on, they really only came up in 6 years ago.
Yes.
2021 now. So thinking about our work or what we're doing is actually the last 6 years. We've come to this point already where our industry partners are seriously exploring using drones, as a commercial solution. Not just as a marketing tool anymore, or just for fun. So that's an interesting point within 5 years that this is possible. So I mean, I think last time we talked about if we're looking at sort of entry markets for drones where it's safe to fly. So for example, offshore applications, where we're not flying over sort of busy airspace or busy lots of people underneath for safety reasons. I believe that's definitely something where we see the application of drones, delivery drones, and so on over the next few years. So 1 to 2 years, 2 to 3 years. Of course, it's a question about autonomous operation, or are these still pilot assisted operations? That's basically what we see, right? Where I would say in 3 years' time we probably can have an autonomous operation. Thinking then about the regulations, so everything needs to be certified and safe. So once we have this small step of the first entry point, I think that's where regulators would come in and actually say, okay, these are robust, safe solutions. Which then would where we're looking at technology for obstacle avoidance, detecting other drones or aircraft, detecting human beings, around potential landing sites, and all these technologies that we need to explore before we can have those vehicles flying safely. So that's something that would be within the next 5 years, I reckon.
And so, do you feel that the development of the regulatory requirements will be driven ahead of the increase in physical lifting capacity, because it's always a requirement, regardless of how light or heavy the drone is.
Yeah, but I think once the regulatory bodies are convinced that the technology works, then at least I hope, then they would be, more inclined to actually look at heavier systems as well. But I think at the moment we are at the point where we're still lacking this let's say supportive technology for autonomous operation, detecting obstacles, so beyond visual line of sight operation.
Yeah.
That I don't think we have many certified drones yet that can operate in that area, and definitely not any heavy drones.
Yeah,
I
for
guess
sure.
those technologies are not trusted at the moment.
Yeah.
But if we look at 5 years down the line, I'm sure there will be a lot more players in that market, providing beyond visual line of sight operations, basically just an add-on box that you put onto your drone that provides this safety factor and redundancy.
Yeah.
And then I don't see any reasons why those vehicles should be limited in their payload as well.
And in some ways, that would reflect what is happening with driverless vehicles.
Yes, yeah, it's true. Yeah.
Okay, yeah, that's interesting, because if we think about air travel, then air corridors and separation, vertical separation, has been around for a very long time. Air traffic control still has a human interface as well, but for drone technology, it's in some ways much more complicated, because that overall global regulation doesn't exist. So.
Yes.
I guess from my perspective, I sometimes think that the development of the regulation and the safe deployment of drones of any capacity, but in significant numbers, is almost as great, if not a greater challenge, than increasing the capacity and capability of the drones themselves.
Yes, that's true. I mean, these are things that we need to explore in parallel. And the good thing is that we have experts doing that. So we have experts sort of pushing the boundaries in the drone design, and then other experts that are very keen actually working on the regulations part as well. But you're right. It's an interesting field to look into, right?
Yes.
We have the regulations. We have all the analysis on what's safe to operate. What's the potential hazard? But at the same time, we have the airspace integration research as well. So as you said, right, moving away from I guess a human operator controller in the loop for the airspace into more automated systems, I would say, where you have drone corridors where they can fly.
Yeah. One aspect of the technology that we didn't touch on, and might be worth exploring a little, is the environmental capability. I'm not in any way familiar with the environmental limitations, other than the very obvious one of wind speed. But I don't know in terms of temperature, in terms of precipitation, hail, snow. Do you have any experience of what the key limitations are?
I mean, so I'm based in Singapore, so we're working with our industry partners here. So I know, I mean, with just the experience flying outdoors and construction site or something, it does happen that the motors overheat and that leads to crashes. So I mean, obviously that's something that we need to consider in the design and the propulsion system and so on, to make sure that this does not happen. I've not dared to look into any, developing any commercial solutions that I would, certify and say this can work in all weather conditions. So of course, if you're looking into rain, thunderstorms, wind, whatever, we see that there are industrial sort of platforms or drone platforms available that basically say you can fly them in sort of light rain. I don't think any of those platforms would promise to fly through heavy showers and have a long lifetime. We're still talking about very sort of sensitive technology So you know, the motors are sensitive to corrosion and so on. So I think last time we talked about operating in sort of offshore environments where you have, you know, salty water. So on, yeah, I don't think many designs right now would be able to operate for a very long time, providing you know, a very cost-effective solution for a heavy lifting drone. So that's definitely something that needs to be addressed.
Yeah, I think you're correct. Obviously, the capability to weatherproof or environment-proof flying devices has been around for a very long time. But every one of those technologies, every one of those mechanisms adds additional weight or additional drag or both, which are all the enemy of drone flight in real terms.
Yeah, that's true. That's true.
Yeah. Okay.
So it becomes a luxury applications, right? So I mean, I was thinking about what's a good application for, let's say, a heavy lifting drone. And for me, I think the market, I mean, obviously you're the expert in where's the potential market for this. But for me, this would be in sort of ad hoc solutions, right? Where you have something like a pop-up drone solution where you need capabilities, you can provide it without the infrastructure in place. And then you move on to your next, you know, site where it's needed. But probably if you're looking at long-term solutions, there would be much more cost-effective ways, right, with a permanent infrastructure in place to provide that solution.
Yes, I think our initial thoughts are very much along the lines of things like delivery of humanitarian aid, where you may have a vessel offshore, 1 or 2 miles offshore, perhaps half a mile offshore, and you have to deliver first aid supplies, potable water, fuel, generator systems, and so on. The areas where perhaps the cost of the operation is far less important than the speed of the operation. But I think as the technology would develop, then we would move to the other end of the scale, where instead of perhaps delivering personnel and air taxis, we may have fixed endpoints in terms of cargo transfer from A to B. And that could be from a ship to shore, but it certainly could be from somewhere in one port area to somewhere further inland, for example. But then again, you do have to be very careful about the airspace you fly through and the terrain that you're flying over. Going back to your point on, you can deliver packages from the port to ships offshore because you're not flying over heavily populated areas. But I think our initial view is that there may be some humanitarian. There are obviously some military applications for that, because most military drones are reconnaissance or strike, and they're effectively unmanned aeroplane type drones, not drones as we consider. So there may be some military operation that would benefit from a heavy lift device as well.
Okay. Yeah.
That pretty well covered everything I want to discuss, Henrik. And once again, a very, very interesting discussion. I think one of the throwaway questions that we are asking ourselves is, given the ever more powerful capability of the Tesla vehicles, is there a Tesla vehicle in existence that has the power to weight ratio to hover?
Okay.
It's an interesting question, isn't it?
That's a good one. Yes. Can I give this to my students? Actually, they can answer this as a
yeah, that would be excellent. That would be an excellent project for them to have a look at. But are there any other areas that you feel we should discuss?
No, I think that's brilliant. That's perfect for my side. I mean, I look forward to all the ideas that you're coming up with.
We'll certainly keep you informed of their papers and their developments. Very much so.
Yes. Also, the battery technologies that you're looking at. You say
yes. We have a call set up with someone who's much more expert than I am in the field of battery development. So we will be delighted to share that with you.
Okay, that's great. Yes. So what's your plan? You mentioned, so you're writing the paper.
We're writing a paper for internal distribution in our own company. And some parts of that paper will make their way onto our social media platform. And I think if that starts to generate additional interest, then we would open up the arena to have further discussions with people who are interested in the technology, perhaps interested in one area of the manufacture and supply chain for a heavy lift drone, batteries, motor technology, airframes, and so on. And I think we would very much let the market plus our own curiosity drive where this takes us next.
Okay, yeah, that's great. So I'm looking forward to this, to the findings, and then
Yes.
of course hope that we can discuss again to see what's happening in this area.
No, we'd be delighted to keep in contact with you. And once again, I've thoroughly enjoyed our discussion, and thank you very much for your time.
Absolutely, and I hope that I can visit you soon in Glasgow when I'm going to Glasgow at least. Yes.
We'd be delighted to host you. Yes.
Okay, that's great.